Hi everyone, welcome to our Data Science. So last time we talked about regression, one of the regularized models, one of the regularized regression models actually extension of logistic regression, and we have actually used this model for prediction of biomedical literature, text classification. We were using that model for classifying whether an abstract is about COVID or SARS publication. So the data, as I mentioned in one of the previous videos, is from PubMed, and we have done text preprocessing and all different kinds of stuff to reach this document feature matrix and TF-IDF and all those information. So for today, I will simply load all these objectives that we have already created in the past, and then after that I will simply proceed to implementing Lasso regression model for classifying biomedical literature. So let me go up and let me simply load this because these are the objectives that I have already created, and let me simply load them and go straight to where my lesson today is. So now today's session is about Lasso, and Lasso is about list, absolute, shrinkage, and selection operator. That's the abbreviation, and Lasso. So it's a main advantage of Lasso is it gives you regularization, and it gives you opportunity to automate feature selection process. So when you do Lasso regression, that means you are doing regularization and also feature selection. You know, if you remember ridge regression, the ridge regression, it mainly does is regularization. So the regularization process, what it does is it pushes all the irrelevant features, the coefficient of irrelevant features towards zero. Although the variables are not relevant, they will still appear in our model. So if you remember, we have 11,136 variables, but they will all be retained in every model, whether you do 100 different lambda values or 1,000 lambda values. While tuning, all these variables will remain the same. They will not change. The only thing that changes is the coefficient values of these irrelevant features. They will be pushed to zero, toward zero actually, not all the way to zero. It will not touch zero, but it will simply approach. It's like a limit. It goes toward zero, but it doesn't touch this. It doesn't cross the zero value. And that's what ridge regression is. As we said, ridge regression is mainly relevant for small data set with correlated features, because ridge mainly controls correlated features. And for today, what we are interested is Lasso. And Lasso, as I mentioned, is it gives you regularization and feature selection. It automates feature selection process. The term Lasso was actually coined by Robert Tipchurani. Maybe if you know this book, I'm sure you will know who is Robert Tipchurani. And this is one of also his colleague and one of the author of this book. And in one of the lectures, he was using this graph. And this is on the y-axis is the interpretability, on the x-axis is the flexibility. And they were saying Lasso is one of the most interpretable model, and easily interpretable. This is the flexibility is, although it's not very flexible, but still Lasso is very easily interpretable. But all the other models, like we talk about, for example, support vector machine, and all the models like random forest, boosting, bugging, and even the fancy deep learning algorithm, they are not really easily interpretable. They are just really black box models. You know, these days people talk about explainable machine learning and stuff like that. Anyway, Lasso is one of the most interpretable machine learning models, algorithms actually, that you can find. So here the objective function of Lasso is calculated by this. So you have sum of square error. This is actually for Lasso regression, not Lasso classification. But as I said, if you understand Lasso regression or the ordinary least square, start from ordinary least square regression, and you extend that principle to Lasso regression, then it will be easier to understand. So sum of square error plus this penalty term, and you have to minimize this term so that you will reach to have a good model of Lasso regression. So everything will from our last video, Lasso, ridge regression, everything will be the same, except that we will change only one thing, and that thing is the alpha value. If you remember, when we do ridge regression, so that we use alpha value of 0. So that means we are telling this geliminate function that we are running ridge regression. But if we want to do Lasso regression, so we change this value to 1. Otherwise, everything will be the same. I mean, you can add some defaults, but otherwise everything will be exactly as it was coded for ridge regression. So I will simply, I have already copied and pasted those that we have seen, the codes that we have already typed together last time. So I will simply proceed. I've already copied and pasted. I will simply run things and see how this model actually works for Lasso. So as previously, so we code Lasso. This is, we give the simple frequency version of our data, train DFMAT, and we use geliminate. And geliminate requires x and y variable. So your x and y variable. So you have your x features actually. So it requires x. That's all the x features, and then the dependent variable or the outcome or the target variable, and that's train include. And then alpha is 1 because we want to do ridge regression, and we give it a family, that's binomial, because we are categorical variable, and 2 classes we are running binomial regression. And you can also do this type measure class. But if you already defined binomial, maybe the type measure may not be relevant. Otherwise, you can also do type measure like probability, but we are interested in defining the class, so we can just use. But if you are like doing I think Rossi curves. You can also define this as probability. I'm not exactly sure, but you can define this type measure as probability. But I mean, we can also check that actually what GLMNet requires. You can simply, as always, you can simply type question mark and then see so GLMNet, and then simply see what actually the GLMNet function requires. So we go to the details and it's a type measure. Maybe it's already there. And we can see type Gaussian, type logistic. Type Gaussian is if you run the ordinary least square regression, and type logistic. And there are other, I don't know, other things that you can have a look. Anyway, you can see this the arguments of this function. I mean this GLMNet function by pressing this GLMNet question mark. So everything will be the same. So we just change this type of data. This is a TF-ID version of our data, and then the rest will be exactly the same. So I would simply run this and see again. This is very fast, so it takes only less than 1 second. It takes less than 1 second, and it's already there. So the next thing is we want to plot this model. So if you remember, when you want to plot two objects side by side, like in one row, but two columns, you can use this C12, and then you define your lasso, because we have already done lasso. Then the x bar will be lambda, and because we want to have a space between the graph and the label, so we are adding this one line space. Then after that, this will be simple. You run it, and you will see this kind of graph. So these are the number of features that we have in our model. We had like 11,000. It started with 11,136, some kind of variables, if you remember from our regression. And they will not be retained, all of them, because Lasso automates feature selection. So it removes those irrelevant features. And from 11,000, we are down to 263. And then it goes to 124. At the end, actually, we only end up with only 2 variables. But this depends where our model is. We will see where our best model, because we have several models. This is several models, but they are tuned by lambda value, because the GLMNet function provides 100 different lambda values. So we have 100 different lambda values here, and our model is somewhere down here. And we will see where that model is. And to see that where that model is, we have to use the CVGLMNet function, and the CVGLMNet is provided using this one. The CVGLMNet is actually, it provides 100 different lambda values. At the same time, it does the tenfold cross validation. So CVGLMNet by default provides the tenfold cross validation. So the first thing you need to do is we need to give you training data. Our training data for the X is train df math. So we define that, and then training root is the Y variable, and type will be the same, the family, and that will be binomial. Alpha is 1, because alpha is 1 is to mean Lasso. And then if you want to do parallel, you can do parallel computing. Parallel equals 2, and by default the intercept you can also keep it. And n-fold is actually the tenfold cross validation. Let's say some people may like to do 5-fold. Depending on your PC, so there is a possibility to change this CVGLMNet. Otherwise, the default is you can keep this off and you can run. That means you are running tenfold cross validation. But if you want to see like 5-fold, depending on the power of your PC, you can do also 5-fold cross validation. But this is where you can control this tenfold and 5-fold. You can simply change this number, and then you can have number of folds. Otherwise, you can simply ignore it. If you are doing CVGLMNet and tenfold cross validation, you can ignore it. And the next one is we do the same for the TF-ID version of our data. So the same CVGLMNet function, and we give the TF-ID version of our data, and the rest of the function will be the same. We just need to plug in a different data set. That means a standardized TF-ID standardized data for the model. Now the only thing we have left is we need to calculate time. So we can simply because we have already defined system time equals system time. So now we can simply see system time minus the time that we have already described before, and we can see how long it took to run this process, or to run this training. Now I will pause. Yeah, it's already finished. Actually, it's very quick. I was actually to pause the video, but it's already finished in 2 seconds. It's very fast, as I said. Now we can print these models and see where actually our best model is. So if we print these models, so the first one, the non-TF-ID version of our model, it's saying the lambda value. That means where lambda value is, this is where our best model is, because we are using lambda mean for prediction. So that will be our best model, where 0.018, this is the lambda value. And then these are the measures and the deviance. And then at the end, we have non-zero coefficients or variables that have non-zero coefficients. So our final model will contain 115 different variables. So we'll from 11,000 something, only 100 variables are relevant. The rest of it is just noise, and this noise is removed by Lasso feature selection technique. So this will be this is very good. You don't want to go through 11,000 variables, but Lasso is giving you only the relevant features. That means Lasso is, if you are interested in variable importance, then Lasso is a good choice. And if you especially have really noisy variables. and the sparse data or something, then Lasso is a good choice. And again, the TF-IDF version of the data is telling us actually the lambda value where our best model is. They are the same, but the coefficients, they are the number of variables that are retained in our best model, they are different. So it's 108, this one is saying 115, but we will see which of them actually works very well for prediction. So the next thing is we want to plot. So we want to plot the deviance, and deviance is the error in the classification algorithm. So we will use, because we are using the extension of logistic regression, so you know binomial deviance, I think. Now if you know logistic regression, so this should be easy to understand. Now we will plot this, and you see where our model is. So now you see in our best model, this is where our deviance is. So this is the minimum deviance. So it starts from somewhere high coefficient, high deviance value, and then while tuning, we'll go somewhere around -4, which is around, actually in the first one is 115. Number of features is 115. So around 115, then this value this is where our best model is. But the one standard error position is here. But this is a model that we're going to use for prediction. Some people, as I said, also use this one standard error, but the most commonly used model is the best model is defined by the minimum error, minimum deviance, minimum error, and that's where your best model is. Again, this is the same is true for TF-IDF version of our data. So this will be where the best model is, and this is the deviance. The deviance value of about I think 0.4 or something. We have actually had it somewhere here. So this is actually the deviance value, I believe, but we can also see where that value is. Let me just see the names. So we have CV, since we don't have the deviance value, but let me just, so CVM, CVSV, CVLO, let me check if it is CVLO. Yeah, so these are all different. No, actually these ones are the lower and upper confidence intervals, actually the lower. And what is the other one? CV up. These are the confidence intervals, but we can see if there are other. So non-zero, these are the non-zero variables, maybe if we want. Okay, this is how they're scaling them. But to be honest, I'm not really interested in this. And then name, maybe. What is name? Yeah, binomial deviance. That's the name of our. You can actually extract these values and replot this. Actually, you can extract all these variables, and then you can do ggplot also to plot this instead of using this. Yeah, it's up to you. So anyway, this is where our best model is, and this is a model that we are going to use in a prediction. So now, as we did for Lasso, for Rich, we will also do a plot. So we have, remember, we have the plot. So we will kind of find where our best model is. This is where our best model is. This is where around here, and in this one again, it should be around here. So we will mark this point with that plot function that we have written here. So now here for that, so what we need is we need to pass this Lasso first model. So let's say if I simply leave this and plot the two, that means it will be the first plot that we have seen before. But I will just add lambda mean. I will mark them, one in red and the other one in blue, and then I will dash them, and then I will also give for the next data, for the next model, Lasso TF-IDF, and I will again define the XVAR, the penalty, the title, and also the TF-IDF version of the data, because I will add the lines, and then I will simply run this, and you will see where the best model is in the Lasso plot. So this is where our model is. The first one is around again here. So this is where it is. Again, on the next one, this will be where it is, where this line is, where the red line is. But if you want, you can also print, for example, actually Lasso. We want to Lasso CV lambda mean. This will be our best model, but we need to pass it again to logarithm. So then we can see log. Yeah, so this is where around close to -3, close to -4. This is where our best model is. This is the model that we will use for prediction. So if we again use TF-IDF, it's the same. I think it will have the same value because this is they are exactly on the same point. But the number of variables they retain at the end of our for the best model is a little bit different. But otherwise, the two models are more or less the same. But again, you can also do this variable importance for this. You can visualize, I don't know, 10 or 15 or 20 variables, and for that we can see BIP Lasso, and then see Lasso CV, and number of features equals 20. Oh, Lasso. This will be Lasso. Yeah, so this is these are the 20 variables that we are that are very important in for the Lasso model. But let's see how the Lasso TF-IDF version of the model is thinking. So let's see. Actually, this should be Lasso CV. No. Yeah. So the first one is telling us SARS-CoV-19 syndrome, and these are the TF-IDF. And then in the second one, these are some of the variables. So it's showing it in bar graph, in bar, but you can also define the geom in point if you want, like the one we did last time. Geom equals point, like this. So the next one will be like this. But if you want, you can also put it like this. I personally like this one, but you can also use this one. And that's because these variables are still there, but because the importance level is very small, it's very tiny, that's why they didn't appear much. And at the same time, this is a equal sign. This is still coming to be one of the important variables for some reason. But when you clean your data, when you do the text preprocessing, you may have to remove symbols. And if we had removed symbols, then it shouldn't have appeared in our model. Again, it's appearing in both occasions, in both of our models. So the next is to use this model for prediction. So we will use these models for prediction. So let me simply use Twitch Lasso, and then define a few things. I think for that what I need is I need to define predict, use the predict function, and then I will simply use Lasso CV. That's what I need, and then after that I need to give it the new X, the unknown data. It doesn't have the label, so for that I will give it actually def matched, I think. Would it like that? Matched. It starts with matched. So that's the text data set that I want to plug in to predict the model. And then S, I need to define this S. That's where my best model is. I think the model that I want to use for prediction. And lambda I mean, that's where my best model is. I want to use a type. Type is equals response. But I want to define another thing, because this will give us two predictions. Actually, this predict function for Lasso, it gives prediction for both COVID and SARS in both probabilities. So it gives us in both. So if I show you, actually if I do this, so it will have difficulties. Lasso, no, this is not a problem. Yeah, it will still predict it. Okay, should be lambda 1, you see, lambda mean, and yes, lambda mean. There's a spelling error. So now it's already finished, but I will have problems, because if I print this, actually it doesn't have any problem. Okay. So it's giving lambda mean. No, it's not giving the prediction. So instead, I want to pass something here like this. This is squared. Because I want to use for the y, so that means I want to predict the. Let me print this one now. Now I can have, you see, this is probabilities for each, so it's giving me the probabilities of the prediction. But I can also define. I think there should be possibility. I think this one is if we leave this, it's giving a probability for both sides of the outcome, like for positive and for the negative. But depending on which side you are, you can decide. For which the prediction is, like, is it for the positive or for the negative. So if you can decide if your variable like 1, if you quote positive by 1, so that means you can define prediction value greater than 0.5 will be close to 1. Otherwise you will turn it down to 0. But that means I thought there is yeah, actually what this one, the type response, what this one does is actually to it gives you the probabilities. So it gives you the probability values. So depending on your class, so as I said, if your outcome variable is coded as 0 and 1, so if your probability is greater than 0.5, then you define it as positive. If positive is 1, otherwise you define it as negative. But you can turn this off. Instead of the probabilities, you can simply define the classes, because you want to have only the class, you don't need the response, and that means you will have the hard classes. So let me run this, and then if I run this, you will see now we have like COVID, SARS, but we can also tabulate this if you want, and then see how this worked. So now we have seen 159 of them are classified as COVID, and 135 of them are classified as SARS. So let me just copy this again and put it for TF-IDF version of COVID. And let me see again, this one will be TF-IDF, and again TF-IDF version of our model, and then TF-IDF version of our data. That's what we need. Now I can simply run it. Now we already have. If I do again to check the prediction actually worked very well. You can simply tabulate the prediction. Again, it's working very well. So now I can simply call conf man lasso, and let me just table first, and then what you do is you can tabulate prod lasso versus the test include, and then after that you do this test include, and then once you have defined that, you can pass the confusion matrix function, and then after that you can add mod equals everything, because you want to print everything that confusion matrix function could provide. Now again, I simply copy this and do for the TF-IDF version. So I call this one TF-IDF, confusion matrix TF-IDF, and then I do this, give it TF-IDF prediction. Now I can simply print this. Actually, this one should be Lasso. Let me copy this and print it again down here. And here, TF-IDF. Now if I run it, I should have the prediction accuracies and all the relevant measurements. But again, this seems to be, Lasso seems to be working very well. So if we look at this confusion matrix, this contingency table, it's an accuracy of 92%, which is very good, and a sensitivity of 95%, a specificity of 90%. Again, Lasso is excellent model. For the next one, it seems it didn't work, but let's see, object from Lasso, TF-IDF, not, okay. Somehow, conf-mat, actually this is Lasso instead of Lasso. So let me define it again, and rerun it. Now you should see again. So the TF-IDF version has improved to 93%. Actually, this is a contender. This is actually the second best model that we have done so far. So it seems the accuracy is almost 94%, and the sensitivity is almost 97% actually, and the specificity is higher than 90%, which seems to be very nice and excellent. Actually, I think the best model we have done so far is SVM SVM with sigmoid kernel. Otherwise, the rest of them are like there are some which touch 90%, but most of them are like 80% something. So again, Lasso, it seems to be a contender of SVM sigmoid, but nothing has beaten SVM sigmoid so far. We will check more models. Again, you know, there is no free lunch theorem. You have to experiment as many models as you can until you decide on your best model. Yeah, so that's all for Lasso, and next we will talk about ElasticNet. So for today, I have already completed. Now I need to save all these objects, so next time I can simply load them and we can reuse them. So let me here come and rerun. So it's loading, and that's all for today. I hope you have enjoyed this session. Thank you very much.